Okay, section 16.8, we talk about Stokes theorem. Stokes theorem is a generalization to 3 dimensions of one of the versions of Green's theorem that we looked at earlier. So we're going to state Stokes theorem and we're going to interpret it and apply it, but we're not going to prove it. The only proof we're going to have of it is the proof that I gave earlier of Green's theorem. So let's start with the statement here. So let S be an oriented piecewise smooth surface which is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Let F be a vector field whose component functions have continuous partial derivatives on an open region in R3 containing S. Before I state the result, which is Stokes theorem, let's just draw this out. Hopefully I have enough room here. So let's see. Say this is S here. And then C, of course, is the boundary of S. S appears to be not even just piecewise smooth, but smooth. Notice that C is genuinely piecewise smooth because C is smooth here, it's smooth here, but there are these little points at the corners where whatever function I have describing C, it's not going to be differentiable there. We've got different tangent vectors there. But that's fine. It's piecewise smooth. Okay, I'm not yet ready to indicate the direction of C. I could indicate a direction, but then I would have to comment more on that. So we'll come back to that issue. But C does have the positive orientation, so that's one of the things we need to talk about. Okay, so here's the result. Then the line integral of C, f dot dr, is the double integral over S of the curl of F dot ds. On the left, we again have an integral that can be thought of as giving the work accomplished by F as a particle moves in some direction, either like this around C or perhaps in the opposite direction. Over here, we have a double integral, a surface integral, not the surface integral of F, but the surface integral of the curl of F across the interior region here. This, as all surface integrals do, is cashed out as double integral over S of curl of F dot n ds. Okay. Let's see, what else do I want to say? We need to make several comments here about that explain what it is that we've actually said. The first is, what does this positive orientation mean? In order to say what positive orientation is, we need to specify a normal vector to the plane, to this surface. Okay, and you recall that for any surface, there's always going to be two, at any point, there's going to be two normal vectors. There's how to draw this. There's the normal vector coming out of the page. In other words, towards us, more or less. And then at that same point, minus n is normal to the surface and goes into the page through the desk, so to speak. And neither of those is sort of obviously the default normal vector to the curve. You just have to specify one of them. And it's not like we're always going to include a negative sign with one and not with the other. If I'm going to call this one n, I have to call this one minus n. I could have just as well called this one n and called this one minus n. So, but let's temporarily put this one to the side and say that n is given. Then positive orientation, you imagine walking along the boundary curve with your head in more or less in the direction that the normal vector goes. And if you're standing, so if we have n coming out of the paper, then you would have to stand on the boundary curve like so. I can't see if that's actually visible there. And then you would have to walk around the surface with the surface on your left. So if n is given, then that means the direction of positive orientation is like this. Because that's how you would move around the curve, keeping the surface on your left. If minus n is given, you have the opposite direction along C. So you would then have to, I'm not going to draw it out or try to think of it. You'd stand upside down, and then in order to keep the direction of the surface on your left, you would have to go in the opposite direction. Just think of an individual standing like this. If that individual is facing this way, if they turn around like this, then they're still facing that way, but now their left arm is to the outside. So they would then have to then turn and face this way. Now their head is upside, they're upside down. Okay, so positive orientation is always subject to some given normal vector. I will just go ahead and state again, this is a 3D version of one of the vector forms of Green's theorem. Remember, one of the ways that we wrote Green's theorem in the plane the integral along C of f dot dr was the double integral over the interior. And actually, what did we call it there? D curl of f dot k dA. So I'm not going to go back into this. I'm just reminding you, one of the ways we wrote and worked problems with Green's theorem in 16.4 was like this. And so this is just, and what we had here was we had a default normal vector equal to k. And so that's why we were able to say in the plane, positive orientation always meant counterclockwise. Well, now that we're three-dimensional, we don't have a default normal vector, so we can't say clockwise or counterclockwise. We just have to wait until the normal vector is specified. Okay, finally, what I'm going to say about Stokes theorem is that it is an independence of surface result. And maybe the way to draw that out would be maybe another picture. So if you're given, say, a cone or a paraboloid, right? This surface here will have as its boundary curve C, and if the normal direction for the if the normal vector to this surface is in the positive y-axis here, then you're going to go around, let's see, to look like that, you have to go in this direction here along C. But you can imagine a normal vector to this surface. The function for that is going to be quite complicated because, you know, at the vertex of the paraboloid, n would be like this, but at various other points, it's going to be, you know, coming out of the page sort of like so. But notice what the theorem says is that if you integrate, if you've got the vector field f and you integrate the curl of f around the surface, that the integral, double integral over the surface of the curl of f is just equal to the line integral of f dot dr. Well, any other surface, like for instance, so if S is the paraboloid, maybe S prime is the disk. And since the disk, which is out here at like y equals 3, right, and has this circle as its boundary, if you take the double integral of the curl over that surface, it's also equal to the line integral of f around c dot dr, because both of these surfaces have exactly the same boundary curve c. But notice what we gain when we trade in the paraboloid for the disk. With the disk, we get a constant normal vector. The normal vector is exactly the same no matter where you are. It's just the unit vector pointing in the positive y-axis, if that's the direction of normality. Otherwise, it would be the constant vector in the other direction. So then when we're taking these dot products with the curl of f dot n, then you've got a really simple computation, because if this is your normal vector, two of its components are going to be 0. So a lot of times the way you use Stokes theorem is to trade out one surface for another. And so you're either going to work problems where they say evaluate the line integral, and then to evaluate the line integral, you'll just switch over here and evaluate the curl over the surface. You might, in the process of doing that, trade out one surface for another. There will also be problems where they ask you to evaluate the right-hand side. They'll say, use Stokes theorem to evaluate the curl. And sometimes when you do that, you might go over here and actually evaluate this path integral over here. But sometimes what you'll do is you'll trade out, use the independence of surface again. So you just kind of have to look at it. Basically, if this thing over here gets complicated and hairy, then you start thinking use independence of surface. And you could use independence of surface on any of these problems. I don't think you're going to see any problems where you have to verify Stokes' theorem or Stokes theorem. Like we did, we had verify Green's theorem where we had to evaluate the two sides independently. For these problems, it's always just going to be evaluating one side, inferring that the other is equal, or using independence and inferring the original surface had the same curl. Okay, so I'm actually not going to work a problem yet. We're going to call this first lecture off at this point, and then come back and work 2 or 3 problems from section 16.8.